Hi, my name is Daniel Aldayev, and I am the Community Champion at Tabsdata. In this video, I want to take you inside of Tabsdata and show you all the key components that make everything work. If you're new to Tabsdata, I recommend watching our introduction video first. You can find it on our YouTube channel, here, and it's also linked in the description below. But Tabsdata is an open source, Python-based data integration platform built with ingestion and transformation in mind. You can think of it as a third space that sits between your data sources and analytics platforms and operates through a pub-sub methodology. Instead of data producers writing data directly into a consumer's platform, they publish their data into the Tabsdata server, where data becomes available to sample and transform at any time. Once consumers are confident in the data's shape and quality, they can subscribe it into their platforms. So how does Tabsdata actually do this? The process begins with a publisher. A publisher is a simple Python function that uses Tabsdata provided connectivity to bring data from external systems into the Tabsdata server. You only need to register the function once, and from that point forward, you can trigger it whenever you need new data. When a publisher is invoked, it writes its output into a Tabsdata table, which is accessible via the Tabsdata UI or command line. Each additional invocation of the publisher produces a new version of that table, which is stored alongside all previous versions of that table. This way, nothing is ever overwritten or discarded, and when you sample this table through the UI or command line, you have full access to the schema and data for every version of that table. So you've published your data, sampled it to make sure that the shape and quality are correct, and now you want to send it to your destination system. This is where the subscriber comes in. A subscriber is also just a Python function similar to the publisher. The difference is that instead of pulling data in and writing into a Tabsdata table, a subscriber takes a Tabsdata table and delivers its data into an external system. When a table has a publisher and any number of subscribers attached to it, they work together like a simple ingestion pipeline. The publisher pulls data in from an external system, and the subscriber sends that data out to its destination. What makes Tabsdata different is how the two connect. In a traditional pipeline, one function calls the next directly. In Tabsdata, they do not talk to each other at all. Instead, the publisher commits its results into a version table. The subscriber watches that table for new commits. When it sees a new commit, automatically runs and delivers that table's data to the target system. This is perhaps the most powerful aspect of Tabsdata. Publishers, transformers, and subscribers are all applied declaratively. So if a table in Tabsdata contains a dataset that is needed elsewhere in your data platform or in a different system altogether, all you need to do is add an appropriate subscriber, and it'll automatically be invoked when the table receives new data. This declarative approach to automatic orchestration allows you to be free of creating new pipelines, orchestration jobs, or managing the data handoff between different tools and systems. All you have to worry about is what you want to do to your data. Tabsdata worries about how it's going to be done. There are many cases where you need to do more than simply move your data. Often, you want to reshape it, clean it, or prepare it for downstream use. This is where transformers come in. A transformer is a Python function that sits between your publishers and subscribers, but instead of just passing data through, it reads one or more upstream tables, applies transformations, and writes the results into new Tabsdata tables. Inside a transformer, you can do common operations like joins, filters, aggregates, deduplication, and much more. You could also do more advanced work, like change data capture or time travel queries across table versions. This is possible because transformers have access to entire table's version history, not just the most recent version, allowing you to make functions that take one version, multiple versions, or even a list of all versions in a table's history as inputs. Together, a publisher that publishes a table, followed by one or more transformers that transform that data into new tables, and subscribers that subscribe that data into external systems, form a typical data transformation pipeline. Such pipelines can be used to conform incoming data to a standard model, apply data quality checks and fail fast when necessary, run advanced preparation routines such as normalization and sanitization, and enforce security and compliance through masking, redaction, and more. The bottom line is that Tabsdata enables you to complete all the necessary pre-work on ingested data so that it's consumption ready in a timely manner. As you scale up the number of data sources, transformations, and destinations in your Tabsdata server, you will want ways to group, organize, and protect your data. This is where collections come in. A collection is a logical container for storing work related to a specific domain. So for example, maybe a collection called marketing would store tables and functions related to MQLs, SALs, and marketing engagement, while a collection called finance would store functions and tables related to expenses, revenue, and profit. Through Tabsdata's role-based access controls, collections can also prevent data from falling into the wrong hands by requiring users to have appropriate permissions in order to access data inside of a specific collection. As your workflows grow more complex, you need confidence that everything runs in the right order and produces consistent results. And there's a lot of work that Tabsdata does in the backend to orchestrate your workflows with surgical precision. When you invoke a function, Tabsdata evaluates the structure of your instance and creates an execution plan. This plan identifies all functions and tables that are downstream dependent to the one being invoked. It then runs those downstream functions in the right order, optimizing the workflow to complete as quickly as possible while also making sure that each table refresh only happens when its input tables are ready. For example, if a subscriber needs 2 upstream tables and one is delayed, Tabsdata will hold the subscriber until both tables are available before starting the run. This framework ensures that results are always deterministic and always reproducible. As long as the inputs are the same, you will always get the same outputs, no matter how long individual functions take to finish. This declarative design prevents race conditions, avoids partial results, and guarantees that downstream consumers only ever see complete and reliable data. While executing, Tabsdata continuously monitors each function in the execution plan. If all functions succeed, the orchestrator updates all tables together as a single update. If even one function fails, the execution plan is paused and nothing is committed until the issue is fixed. This guarantees what Tabsdata calls a pristine state, meaning that every table in your instance is consistent and trustworthy. When teams sample data, they know what they're looking at is accurate, complete, and never the result of a partial or failed execution. So let's walk through an example to see all of this in action. Imagine your team wants to send customer data from an Oracle server into some AWS Glue Iceberg tables. You would start by creating a Tabsdata instance and then set up a collection called customer data. Inside this collection, you'd build an Oracle publisher function, and in the function decorator, you would define the authentication and query for the Oracle server. You would also define the target Tabsdata table where the data will be written, in this case, a table called customers. Next, suppose you want to split the data into new versus old customers. You would then create a transformer function, and in the decorator, you would specify that it reads from the customers table and outputs 2 new tables called customers created this year and customers not created this year. In the function body, you would add logic to separate the data into those 2 groups. Finally, you'd create a subscriber function that takes those 2 tables and writes them into AWS. Once all these functions are registered, you simply trigger the publisher function and wait for Tabsdata to handle the rest. From the user interface, you can then navigate to any one of these 3 tables and inspect their latest commit or review previous commits if they exist. And those are the basics of Tabsdata. For more information, please feel free to explore tutorials and documentation at tabsdata.com. We are still early in our journey, so if you want to see anything happen, let us know in our Slack channel.